Hello everyone and welcome to this 23rd European Conference on Fracture. Thank you the organizers of this great conference for the opportunity you have given me to speak today in this great gathering. My name is Emilia Chiamaka Ikenna-Uzodike, a PhD student at Lancaster University working at CWI, the Wedding Institute, and National Structural Integrity Research Center, Cambridge, United Kingdom. Today, I will be going through an industrial approach to high strain rate testing, and I'll be talking you through this topic today in this great conference. My co-authors are also on the screen, Janin, Pedro, Win, and Marius. I hope you enjoy the rest of my presentation today. We'll be showing the abstract for this conference, which I will not be reading through. This abstract is contained in the program of the day. And we're talking about some of the approaches we've applied industrially to measure high strain rate testing. And on this, we have used some methods like instrumented choppy testing, the impact testing, and the servo hydraulic testing machine to be able to measure high strain rates loading test. And we also applied some computational analysis and also the analytical model to also analyze some of the results. We went ahead to use the artificial intelligence for this. Let's start by showing some of the examples of the experimental setup which we have utilized in this project. Here we can see that we have the hydraulic machine, and you can see the flat tensile specimen on it with speckle patterns around it, and this is used to be able to utilize the camera when it's capturing for the digital image correlation analysis. We also have the 3-point bend specimen here, which we use for the choppy test and also for the impact testing. These are used in order to obtain mechanical properties at high strain rates, such as fracture toughness and then the ultimate tensile stress. We utilize the digital image correlation to analyze the results which we've gathered from the experiment. Since it is difficult to use the traditional approach for strain gauge to measure the strength in this experiment, so we utilize the speckle patterns and then camera, analyze it in the GeoM software to obtain the strength. And as you can see in this video, how the material started and then up to fracture. So this material propagated and then fracture, and on the here we see the curve which we have obtained using the data points from the GeoM machine, and then from there the applied force. We utilize the approach of thermal diffusion to be able to measure the ultimate tensile strength. Since there is a little much difficulty in obtaining the ultimate tensile stress in this material, so this thermal diffusion distance was calculated using the thermal diffusivity of this material. The material we are using is the X65 grade steel of 0.1% carbon content. So this thermal diffusivity value is assumed to be 18.8, and then we have test duration for the whole test. For the quasi-static ones, we have a higher test time, and then the highest displacement rates like 5.4 up to 15 meters per second. We have the thermal diffusion distance, as is the higher the strain rate is going, the lower the thermal diffusion distance. And because this thermal diffusion distance is recorded as short interval, this high strain rate will be considered as adiabatic process. We can see on this slide about 4 different strain rates which is applied, and the static one here has the thermal diffusivity up to 200, and it continues all through the experiment such that the ultimate tensile strength is obtained later during the experiment. But for the case of the high strain rates, we see that the ultimate tensile strength is reached at the first part of the test, and before thermal softening starts in the material due to the increase in temperature. And this has made us to measure the ultimate tensile strength at the beginning of the experiment, after which there is decrease in the stress applied, and then there is increase in the ductility up to 3 times that of the strain rate. Here we can see the different mechanical properties obtained. The Young modulus, which is about 207 to 210 for the quasi-static testing, and for the dynamic one, we have the range from 240 to 460 depending on the strain rate. The 0.2 proof strength is also increased from, we have the 640 to 688 in dynamic one, and about 480 to 500 in the quasi-static one. The ultimate tensile stress too is also higher, which is about 740 to 855 in the dynamic one, and then lower about 600 in the quasi-static one. So we can also see the increased elongation in the dynamic one, because it's higher due to the fact that we have a higher temperature, which increases the elongation but decreases the strength of the material. We went ahead to utilize the analytical model to model the plastic deformation of this, and we utilized 3 of these models. So the first one we use is the Johnson-Cook model, which the equation is given here, the flow stress. The constant parameters are determined from experiments using different approaches. We use the reference strain here as 8.2 to 10 raised to the power minus 5 for the strain rate. From the experiments, we derive the parameters for A, B, the N, the C, and M constant. We only concentrated on the room temperature and didn't use any other temperature for this work. We could see the graph here. It shows good correlation with the experiment and then the Johnson-Cook model calculations. We also utilize the dislocation evolution model, which we have the flow stress and the density, dislocation density. So the equation here embedded the phonon drag effects here in this equation, which is the first part of this equation. And then we have different values for alpha, and for this material it ranges from 0.05 to 2.6, and we can see also for the different strain rates here, the graphs related very well as they propagate. The third one we utilize for the analytical model is that of the cosmetic formulation for BCC model, because the material we are using is the X65 grade steel, and it's a BCC, the body cubic centered material. So we use the dislocation storage coefficient K1 here, and then the dynamic recovery coefficient, the FBC here. So with this equation, we obtain the flow stress too that will be undergoing at different strain interval. The 3 analytical model in correlation with the experimental value are shown at different strain rates here, which we use different 4 strain rates here, and we could see there is a good correlation for the 3 model and the experimental one. We went ahead to use the final element analysis for these high strain rates, how the hammer is dropped at different velocity, and then we have the recording. Let's see how this propagates. We could see that the hammer dropped from a distance until it's getting contact with this specimen, and then it continue until fracture propagates. I won't forget to mention that we utilize different notch, which is about the 5 mm notch and also the 2 mm notch, as we've seen in this simulation. The another approach we use is the artificial intelligence method, which we apply the machine learning algorithm using some features from the experiment. Here we utilize the crack length, and for this app, the crack length which was created using the EDM notch. So we have different values for the EDM notch, and also we have the pre-crack ones which was done using fatigue pre-crack method to induce the crack in the experiment. The apply force for different experiments as well, and then the KQ for the materials which we are using, also because we are trying to predict the fracture toughness. So this shows the partial matrix for the features which we have used, and we could see that it has good relationship, except for the the pre-cracked ones, which has some lower value due to the fact that some of the materials are pre-cracked while some are not pre-cracked. So we proceed to use this to predict the fracture toughness. And we have here the results which we have obtained from the algorithm. And we could see the true toughness, which is on the x-axis, and the predicted toughness on the y-axis. From this, we could say that there is an agreement in this, and then it is sufficient to utilize the machine learning to predict the fracture toughness of material. In conclusion, we've seen how different methods has been applied to measure high strain rate testing, using the Chappy, using the Istrom machine, and also we have also applied the high-speed camera in the digital image correlation to obtain the strain in the material, and then we were able to obtain our stress strain curve using the point data which we have obtained from this method. The analytical model was applied to, and also the computational method, as well as the artificial intelligence method. These are used for predicting, and then we correlated the experimental results with them, and we could agree that there is a quite reasonable correlation between these methods and that of the experiment, and that is to say we could predict using this method the fracture toughness of material at different conditions. The last point we want to point here is the limitation we experienced during the use of machine learning. We have here the data because we have limited number of data for this, based on the fact that the data come from experiments. So it's very expensive to run some of these experiments, and we couldn't get as much data as possible. We hope to add more experiments and then more data to be able to enhance this model and make the prediction accuracy better. So thank you for listening to my presentation today. And we have our contact details on the screen there in case anyone wants to reach us for any question. We are very happy to answer any question. And we thank our sponsor, the Red Register Foundation, for the support they've given us all through and the provision of materials. I won't forget to thank the organizers of this conference once again. And then I hope everyone enjoys the rest of the conference. Thank you.